All right, I'm going to go ahead and start the recording. And so, welcome everyone. And as soon as Zach starts sharing his screen, we'll go ahead and get started.
All right, let me know when you guys can see it.
Yep, got it.
Perfect. All right, let's move some things around here so I can see everything I'm going to be talking about. All right, so tonight I'd like to give everyone an introduction to MLOps. As I mentioned, my name is Zach Hine. I am a data engineer with Steampunk. I'm working primarily on ETL and MLOps. So tonight I'll be breaking up this talk into three main areas. First, I'll give a quick background into our work with data exploitation at Steampunk, then give an overview of the MLOps framework, and finally walk through a demo of what this all looks like in practice. Given the size of the meeting here, I'm going to try and keep it pretty informal. If you have any questions as I go along, feel free to ask. We've also left some time at the end for some Q&A as well. But like I said, we can keep this pretty informal going forward. So there are a few terms I'll be using throughout the slideshow. Data exploitation is a term we use at Steampunk to define our technical competency focused on providing a full spectrum of data capabilities, which I'll go into deeper on the next slide. It just refers to the wide range of data-related services that we offer. I think most people here are familiar with DevOps, but we can also extend that to DevSecOps, which automatically bakes in security into the software development lifecycle, enabling the development of secure software with the speed of DevOps. And finally, we have a concept of design intelligence to generate human-centered solutions, which means we want to deliver products and services that are grounded in the understanding of the people who use them. And I know it's cliche to say that we want to think from a user's perspective, but we all know in reality that final product doesn't always seem that way. So what we at Steampunk think is the most critical is building holistic data solutions that are user-focused. So combining DevSecOps with data exploitation with a focus on users led us to create two major playbooks that we use in our data solutions, those being DBOps or database ops and MLOps, with DBOps focusing on data engineering and MLOps focusing obviously on machine learning. So we have actually both of them at Steampunk. So these are some of the core capabilities that I mentioned earlier, and I wanted to show how DBOps and MLOps overlap with these. At the bottom, we have data strategy, which involves identifying data sources and where it should be going. The next layers essentially fall under data engineering and automating the ETL process. And at the top, we have business intelligence capabilities of data science and visualization. At a high level, we can think of the data engineering capabilities falling under DBOps, while MLOps encompasses primarily data science and visualization. But I think there are aspects to both, all these capabilities within both MLOps and DBOps. So what we have here is a DevSecOps pipeline with the steps of development, building, testing, pre-production, production, and maintenance. And if you take this pipeline and create it solely for the purpose of crunching data, working more on the data engineering end of the spectrum with data platforms, what you get is the DBOps framework. Whereas if you're working more on the data science end of the spectrum, you get MLOps. And the reason why this is critical and useful is that we are able to borrow some of the niceties from DevSecOps and use them in the data exploitation world. Things like code repositories, automation, testing, being able to do peer reviews on code, containerized applications, and so on and so forth. All of these are concepts familiar to DevSecOps, but not really being applied to data exploitation. And so being able to do this with the frameworks of DBOps and MLOps allows us to build much more robust data exploitation work and improve the quality of our code. So that's just a quick background to some of the work we've been doing at Steampunk. But right now, our focus is mainly on MLOps, and obviously that's what you guys are here for tonight, so that's what I'll dive into. I'm willing to bet that most of you have heard the phrase machine learning, but there are various levels of understanding as to what that means. And I think almost nobody has heard of MLOps. So today, hopefully I can speak to what MLOps is and why it's useful. To that last question as to why it's useful and what it has to do with you if you don't normally work with machine learning, whether you know it or not, just about everyone here has interacted with an MLOps framework in production. Netflix uses it to identify trending shows and offer what you should watch next. Amazon uses it to recommend other products to buy on their platform based on your purchase history. And Google has personalized ads that are tailored to you using machine learning. So let's take a step back and level set as to what ML is before getting into some of the more complex details. At a high level, machine learning is the development of computer algorithms that improve automatically through experience in the use of data without being explicitly programmed. So what that last part means is if I buy a book on data exploitation on Amazon, a software engineer doesn't go in and manually alter my profile to recommend similar books. The ML system does that automatically based on the model and the experience with other users' purchase history. To be able to do this, we start with a bunch of collected labeled data and split it into a training set and a test set that we hold back. We then train a model based on this training data and evaluate using the test data to see how it performs on data it has not yet seen. If we're satisfied with that performance, we then deploy it in production to make predictions on new data that has been generated with no labels, and then we can save those results. So this is a diagram of a single machine learning experiment that a data scientist might run. There is a data store that they can extract and analyze the data from. They can prepare that data manually, like cleaning it, dropping null data, things like that. Then they train the machine learning model, evaluate and validate that model against, like I said, the test data. And if they're satisfied, they can take that trained model, save it into a model registry, and then serve that model in a prediction service to generate new predictions. Now, this type of experiment would probably involve writing custom code that is tailored specifically to the data and the type of experiment being done. And if there are several data scientists all writing their own code and doing experiments, it can quickly become difficult to keep track of all the code and metadata regarding these experiments. Reproducing these individual experiments independently verifying the validity of the model can be pretty difficult without knowing the exact details of the parameters used. Additionally, an ad hoc experiment to quickly solve a problem probably does not contain enterprise-worthy code, and we would want to limit the amount of that circulating. And this is really where MLOps comes in. I know the slide is a bit busy because we're going up a level in complexity, but bear with me, I'll walk through it. The two main goals of MLOps are to create a repository of ML models that can continuously be retrained and reused, as well as automate and increase efficiency for many of the steps that data scientists would normally have to perform manually. And the implementation of MLOps contains several elements to help solve this problem. There is a registry that contains predefined source code for a variety of models to be used. This code is then used for automated machine learning pipelines that perform all the steps in the experiment down here. The metadata regarding these experiments, such as who ran them and when, are stored in a metadata repository. And there's a feature store that increases speed and reliability and consistency in machine learning by allowing data scientists to draw from the same feature code base. And finally, machine learning models are only as good as the data they were trained on. So we need to continuously monitor the performance of the model and create triggers that will retrain the model when the performance degrades. An example trigger might be if the statistical distribution of the source data has been altered. For example, if you had an ML model that predicted hotel room occupancy, but it was trained on pre-COVID data, that performance has probably gone down over the past year or so. We are bringing all these elements together to allow data scientists to create reliable, automated machine learning pipelines. So a major challenge when it comes to deploying MLOps in a production environment, whether internally or externally for a client, is the need to utilize and bring together many different tools that are needed to cover the range of tasks we've talked about so far. As mentioned, we are merging the field of data science and DevSecOps, and the tools that have already been developed to assist with these areas were not designed with a holistic approach to data exploitation that we are trying to achieve. For example, let's look at some of the tools that we can use to fulfill or to implement the full MLOps framework. For example, we might have a feature store that's using a Postgres database. We can use pandas, which is a Python library for the data analysis. There are data validation tools out there like Great Expectations or Apache Spark for data preparation. Some libraries can be used to complete several steps in the process. For example, scikit-learn can be used for both model training, model evaluation and validation, and model analysis. We use GitHub at Steampunk as a source code repository for cloud hosting our code. We use Jenkins for continuous integration and continuous delivery. And we use Docker as well. We can deploy Docker containers containing these applications for use anywhere. Again, MLFlow is a library that can be used again for many different steps in the automated pipeline. We use workflow orchestrators such as Apache Airflow to organize, orchestrate, and automatically trigger these automated pipelines. And then we can use Apache Kafka for performance monitoring and to identify triggers for when we want to reuse or rerun these automated pipelines. And the key thing here is this is by no means the only way to do it. For each step, there might be a few open source tools that can be used to complete the task, not to mention those developed by private companies. So the different combinations of tools and libraries is pretty extensive, obviously. So you might be thinking those are nice boxes in a PowerPoint, but what does this mean in practice? So when I first started, I had a hard time wrapping my head around it as well. I was used to doing those single machine learning experiments with no real tracking or automation. So hopefully I can demystify it a little bit with a demo. I'm going to set up what we're going to try to accomplish in a few slides and try to make it relatable so I don't overwhelm everyone with code, and then I'll show it in action. So the first thing that any ML experiment needs is a business use case and enough data to draw conclusions. For this experiment, we're using an example from biology. We want to develop a model that can identify the species of iris flower based on the measurements of its petal and sepal. On the left here, we have 3 of the species of iris that we are looking at: Setosa, versicolor, and virginica. And on the right, I have a subset of the 150 flowers that were measured out in the field. The measurements are referred to as features or attributes, and the species is called a class or a target. Each individual flower is referred to as an instance or a sample of the data set as well. So this is a very commonly used data set for introducing machine learning, and hopefully this chart shows why. I've plotted each of the 4 features against each other and colored the points by their species. Hopefully just by looking at this, you can see that the species are clustered pretty close together depending on what features are plotted. As humans, we would look at these plots and say, well, the flower has a petal length less than 2 or a petal width less than 1. It's definitely a Setosa. However, it might be quite a bit harder to distinguish the boundary between versicolor and virginica. As you can see here, these are pretty closely tied together, and that boundary is a little bit hard to distinguish. That's really all machine learning is, getting a computer to recognize patterns or correlations that people can intuitively see, as well as those we might have a tougher time distinguishing. Okay, so how are we going to do this? To classify these flowers, we are going to use a machine learning model called a decision tree classifier. I chose this type of model because it's intuitive to visualize and explain. A decision tree is just a method of narrowing down our data until it is grouped in sufficiently homogeneous batches that we can confidently classify it. For example, let's say I'm holding a piece of fruit for my breakfast that's either a banana, apple, or an orange. And I ask you to guess what it is, and I'll only give you yes or no answers. This might be how you go about narrowing it down. You might first ask, is it round? And if I say no, then it's definitely a banana. If I say yes, that's not enough to distinguish the last two. You have to ask another question, is the color orange? If I say no, then it's definitely an apple. If I say yes, then obviously it's an orange. You're using the features, in this case, the shape and color, to determine classification. So unknowingly, I bet most people here have used a decision tree classifier. If you've ever played the game 20 Questions or the game Guess Who, those are decision trees. You're just using the features of the characters here to narrow down until there's only one left, and you can confidently say who it is. Before I jump out of the slideshow, I just want to give a quick intro to some of the tools that you'll see here in a second. As I mentioned before, we use GitHub as the code repository and version control in the cloud. As Python is the programming language most commonly used for data scientists, and that's what I've written this little demo in. Apache Airflow is an open source workflow management platform for task scheduling and automation. And then finally, MLFlow is an open source machine learning management platform for tracking, registering, and deploying models. So you'll see all of these in a second here as I jump out. So I'm going to hop into my browser and pull up some code here. Okay. So right here, I've written essentially 5 small functions that go through each of the steps in the machine learning process that I mentioned previously. So I'm loading the data here, prepping it by dropping any columns and cleaning any data that I need to, and getting the labels for that data. I'm training a model, scoring the model, and then registering the model once I'm happy with it. And then finally using that to predict the model or predict the data on, predict the label for data that I have not seen. So for example, here I've loaded the data. You can see here are the 150 different flowers that have been measured with their features, the sepal length and width along with the petal length and width, and the species of flower here. So I load that data, split it into those training and test sets that I mentioned earlier. I train a decision tree classifier, train that model, score that model, which has an 86% accuracy, which isn't too bad. And then down here, I have a new data point that the model has never seen before with these measurements for the flower. And if I feed that in, then my model predicts that this new flower is Setosa. So what I've just done is created a model that has never seen this particular set of measurements before, but just based on these numbers and using pattern recognition, it has output a predicted label of the Setosa species. So what I'm pulling up here is essentially, let me expand that or increase the size of this here. Sorry, the Zoom bar is overlaying the size bar. Okay, or not. Sorry about that. Let me see if I can move this. Let me just do this manually. Sorry about that. So basically what I'm showing here is the decision boundaries from that model. So you can see everything. So that's not very helpful here. But as you can see, everything with a petal length less than about 2.5 here, and this red is classified with these red dots. I think that's when I say Setosa. Every point that falls in this yellow boundary is getting classified as yellow, and everything is green. Everything obviously in green is getting classified as the green species here. And as you can see here, what has happened here is this decision boundary isn't very good, and there are a few green dots that accidentally have fallen into the yellow portion, which basically means that these dots have been incorrectly classified, which means my decision tree classifier is not performed as well as I might hope. These are incorrectly classified points. And I've done this intentionally to show you how MLOps is used to improve our model. So now that I've created an initial model, what I would do is push it to GitHub. Again, let me see if I can hide this here. Okay, sorry about that. So I can create a model, push it to GitHub, where it can then be cloned and run from Docker containers anywhere people want to run this. And here I have an Airflow, what we call a DAG, which is a directed acyclic graph, but it's a list of all the tasks that I need to run to essentially trigger and train my model again to rerun the MLOps pipeline. So again, I've loaded and pre-processed the data, fit the model, generated or read new production data, loaded that new data, processed it, updated my model, and then saved this all off to an archive. So if I trigger this here, basically what's going to happen is I can schedule this set of tasks to run automatically, whether daily, weekly, or just based on whenever my statistical distribution has changed, to update my model and save off a new model with improved parameters that will increase the efficiency of my pipeline. So hopefully that makes sense in that I start off with a single model. It may not be performing great, but it's working, well enough for us at the moment. But over time, we generate new production data, and we can set up workflow orchestrators that automatically run and retrain the model and update it. And if the data is or if the model is valid, it pushes it to production here. As you can see, it's running through each of these tasks. So the next thing that I'll quickly show is I mentioned MLFlow, which is which tracks and stores different model runs. And this is what we're going to use to essentially notice if one run, a new trained model, is better than the previous model that we already have in production. So in this case, I saved off one of the runs I've already done. It has all the parameters that I'm using for my machine learning model, has the current metrics. And in this case, because the value has not improved, the model from this run did not replace the current version. If I go back here and go back to a previous run, as you can see, I've got a lot here. This one is not replaced. But in some cases, see, sometimes we'll have runs that will replace previous versions of the machine learning model here. So I think this is one here. So you can see the previous accuracy was 0.82. The updated model has an test accuracy of 1 or 100%. So in this case, the status, the model from this run replaced the current version. So we have had a model in production, retrained it, had a better accuracy, and MLFlow automatically replaced this current version with the updated model. So if I go back here, see if my pipeline has completed. And if I go into here, if I zoom in, what you should be able to see is these decision boundaries have improved. So my classifier is now correctly classifying these instances that were misidentified earlier. So we've improved the decision boundaries to correctly classify these incorrectly classified instances from earlier. So that's an example of how MLOps has been used to improve the efficiency of a machine learning model in production.
So Zach, on that, before it looked like it was using solely pedal length, like the original one.
Yeah.
Is what it's doing here, although we're looking at pedal length versus sepal length, is it using some other criteria now to pull those out, or is it actually doing all sorts of ranges to try to cherry pick those individual green points?
Yes, it's using, good question. It is using all of the 4 features that I previously mentioned. This is just for visualization purposes that I plotted these pedal length and sepal with. You know, obviously with 4 features, I couldn't create a 4D visualization. Instead, I'm just using 2D to show how the decision boundaries change using all of the data and an improved classifier to kind of pick out these incorrectly placed models from previously. So I think, you know, here previously, again, expand this, these green points on the yellow background are incorrectly classified points based on all 4 features. But with the improved model, we've adjusted the decision boundaries. In reality, these might be 4D decision boundaries, but obviously that isn't very good for visualization. Instead, it's just the 2D ones that I plotted here. But they've fallen in now this green bucket essentially.
So this wouldn't be considered overfitting?
Good question. In this case, yes, I essentially deliberately overfit the model here for visualization purposes. But that is a great question. Generally, in both training and testing instances, you never really want to get 100% accuracy. You should have a few, I guess, misclassified instances for when new production data comes in. I think it's really impossible to, if you do, or it's not impossible, if you do have 100% accuracy, that's generally a sign of overfitting. In this case, that is something I overlooked. You know, just based on you know, going into overfitting, I wasn't sure if everyone's familiarity with that concept, but I can definitely talk more about that. But yes, in this case, I have overfit just for visualization purposes.
And what's the danger of that, or what's the problem that creates?
So the danger that overfitting creates is that when you overfit, you essentially get these very specific classification criteria. So in this case, you know, this little box here, it's very specifically fit to this one data point. And obviously in real world data, you know, this might just be fat fingered. This might be incorrectly labeled data, or you know, this might be data that wasn't actually meant to be here. And if we start creating these little specific, you know, very general or very detailed criteria to, you know, fit this point here, what's going to happen is it's going to miss other data kind of in this area that should be classified as, yellow here in this case, but gets classified as green because we've overfit the classifier to basically pick out this point to get 100% accuracy, if that makes sense.
Yeah, and it's because it's only test data and not the actual data, right? We're going to see other points that, like you said, yellow ones that might fit in that green square.
Yeah.
That we would have clearly picked up without the, with the previous model would have clearly looked like they should be yellow because they're right in that yellow section, which was, a good fit, but not as specific as this one. Okay, thank you.
Yeah. And a common technique to avoid that is what's called cross-validation. And what that essentially is that you retrain the model multiple times, but hold back different test sets. So in the first, validation, a common type is like five-fold cross-validation, in which you break it up into like 5 different training and test sets. So for the first set, these points might be held back. In the second set, a couple of different points might be held back. And then you essentially kind of average your accuracy. And that prevents, these one-off instances from being included in the classification. By kind of averaging over a variety of test sets and training sets, you can avoid overfitting. A great question in regards to overfitting as well. It's something that I deliberately didn't talk about, but it's definitely a very it's something any machine learning engineer needs to be cognizant of, especially if you're not too sure what the incoming production data might be or how it might change over time. So on that note, I think that that kind of goes through everything that I had ready to present. A couple great questions so far. Are there any other questions? I said I'm going to open up this time kind of for just a freewheeling discussion about anything related to MLOps or machine learning. If you just want to have any questions or discussion.
Do you have any general advice for someone who's interested in transitioning into an ML engineer position?
Great question. So I would say my advice would probably be, like I mentioned at the start of the demo, try and find a business use case that you think might be ripe for machine learning that maybe isn't currently being used. If you have a database at your company that has a lot of labeled data or a good data set that you might be able to leverage that isn't currently being leveraged, and just try and play around with it to see, are there any patterns that I can pull out that might be used, for business intelligence? Is there trends in sales or something like that that I might be able to discover from this set of Salesforce data or something like that? I know that's pretty vague, but I would say, depending on the company, unless it's like a really cutting edge tech company, like I mentioned, like Amazon, Netflix, Apple, one of those, the big five. Most companies have a lot of data, but are still just in the very early phases of really utilizing that data and gleaning as much insight from it as they possibly can. So, maybe your company doesn't have any machine learning engineers or hasn't used machine learning yet, but is interested in getting, into that sphere. I would say kind of just take it upon yourself to try and generate a use case. And there's a ton of kind of walkthroughs online for how to create and train a model, use that as a template for creating a presentation similar to this and present it to higher people in your company. And then maybe if they're receptive, great, and if not, you have experience that you can then take to another company of how you created this machine learning experiment and generated insights from data, if that makes sense.
So Zach, if it's, oh, sorry, go ahead, Radita.
I said, yeah, it makes sense. Thanks.
So if it's not too much proprietary information, what are you using the machine learning and the MLOps for at Steampunk right now? Since I know basically that the type of work we're doing there, but is it related to security vulnerabilities? Is it related to data that they're pulling in from other areas? What are you really doing with it?
So right now at Steampunk, we're creating the framework that will allow hopefully any data scientist to pull from a feature store, like I mentioned, and use the framework to deploy the pipeline and run their experiments continuously and save them off for any experiment they want to run. I know, I think the idea is, at Steampunk, we have several different clients, all who have, data scientists on their staff running different experiments. And I think at Steampunk, we want to both be able to offer the machine learning expertise in terms of running those individual experiments if they need that, but also just give them the framework to, like I mentioned, the code repository so that they can pull the code, deploy these Docker containers, and be able to run these experiments automatically without having to kind of go through that manual data science process of, okay, here's what I need to do. Let me write up a Python script, run it. Oh, it's not very good. I need to adjust the parameters. Let me save this, save this script on my local computer and rerun it again and then deploy it, but I don't know what parameters I used previously or what data I used. All those problems with running ad hoc experiments, trying to provide a framework to clients to generalize and automate that process so it's not quite as messy.
And so you're kind of expecting teams to show up with, I have all this data and I want to start being able to do predictions and stuff with it. How do I take this data set I have and start turning it into something I can use to predict stuff in the future, right?
Exactly. I don't think we're even at the use case yet.
Okay.
Clients have the data, and I think we want to be able to help them through each step of what can I do with it? Can I, is this something I can run machine learning on? Not every problem is a machine learning problem. Mm-hmm. There might not be patterns to the data. It could just be random. Mm-hmm. But we want to be able to both identify if there is an opportunity for machine learning, set up the framework, get them started, and then hopefully by the end, kind of let it be running and kind of hands off, and then only monitored every so often. And maybe a data scientist comes along and is able to come up with a better model. For example, going from a decision tree to a neural network, being able to then just simply push that code and use the DevSecOps framework to have that automatically deployed without much heavy lifting on their part.
That actually brings up a question. This was a great demonstration because you showed kind of how it starts narrowing in and taking the set of data. But what if it is random? What if it never can converge enough? How do you kind of detect that? Is it just that you just never see it converge? You just never see it get better at the accuracy? Or
yeah, I mean, I think there are a few different ways. I think you can get into, that's where I think overfitting comes in. I think given a set of data and a machine learning model, you can tune it in some way to generate what it thinks is a pattern. You can get an accuracy that you think is satisfactory, but I think it really comes once you're in production, it'll fall apart really quickly. And if it's the kind of thing where your model is being retrained and the accuracy is falling pretty quickly anytime new data is added, that's, I think, a signal that maybe your model isn't as robust or effective as you think it might be. If any time new data added is enough to throw it off, then maybe that model isn't really designed that well in the first place, and it was just overfit, and new data is failing almost immediately. I think that might be a signal that, hey, maybe machine learning, or at least maybe the current model is not ideal. I think that's another difficult thing, is that not every some problems lend themselves to certain types of models and others don't. For example, a decision tree classifier wouldn't be used for image recognition, but a neural network would be. And so just because I can't classify my photos using the decision tree doesn't mean necessarily that that's not a machine learning problem. It's just I need a different approach and a different framework to implement.
Yeah, I actually I judge the local science fairs here. I'm one of the judges, and one of the things we see a lot in we do the computer projects, right? And a lot of them are machine learning. And one of the things that, although I don't understand how it works, but one of the things we see a lot is they'll get the students will get a data set, they'll train it, almost always using, a couple different Python scripts and loading the data, and, they'll load all the data, build a neural net for it, and then they'll throw it back in and show that it all matches 100%. It's like, well,
Yeah.
it doesn't really show anything. I mean, I understood enough to know that if you're feeding the same data back, whereas the students who understand it better definitely, they'll hold out, they'll hold out some of the data that they'll use, and they can show that they can, the last, I don't know what it is, whether it's a fifth, I think is what you said, they'll put in 4 sets of data and it'll tune, and then they'll put in a 5th set and it'll come back with, 85 or 90% accuracy. And that actually seems like, it was a reasonable thing, right?
Yeah.
If they come back and say it's 99, it doesn't sound like it's a reasonable match. It sounds like they just, like you said, overfit. So
Yeah. And that actually brings up another common problem in machine learning, which is what's referred to as unbalanced data sets. A very common example of this is fraud detection for credit card activity. So if you think about it, large credit companies, for example, Capital One right here in Virginia, they use machine learning to identify fraudulent credit card transactions. But 99% of credit card transactions are not fraudulent, right? There's only maybe 1 out of 1,000 are fraudulent every day. So if you just said that, if you had a set of data, you just said every transaction is not fraudulent, you would be 99% accurate. But that's not really helpful for what you're trying to do.
right.
That sounds great. You're like, oh, yes, it's 99% accurate. But my mom just said, I never have a fraudulent purchase. That's true, but that is missing the key that you're looking for. So it sounds good. The 99% when it pops up on the screen looks great, but digging a little deeper, not exactly what you were hoping for or what your goal was in that use case.
Cool. Anybody else with questions? All right. Well, Zach, thank you very much. This was very helpful.
Yeah, I appreciate it. Like I said, if you guys have any other questions, feel free to contact Jeannie, you can pass them on to me, but it was great talking with you guys tonight.
Thanks a lot.